Imagine floating in the pitch-black void of space, your spacesuit the only thing standing between you and the endless vacuum. Suddenly, a tiny crack forms in your visor, just a hairline fracture, barely noticeable at first. But in the blink of an eye, the pressure difference rips it wide open. Your oxygen screams out into the abyss, your body screaming with it. This isn't science fiction. It's one of the terrifying realities astronauts face every time they venture beyond our atmosphere. Space doesn't forgive mistakes. It doesn't offer second chances. And while we're captivated by the beauty of distant galaxies and the promise of discovery, the truth is, space is hiding dangers we rarely talk about, dangers so extreme, so unexpected, they could turn a routine mission into a nightmare in seconds. We've all seen the heroic footage of launches, the stunning views of Earth from orbit, the triumphant landings. But behind those moments of glory lies a world of hidden risks, from deadly radiation storms to the psychological toll of isolation, millions of miles from home. Think about this: every time a rocket leaves the pad, it's not just carrying astronauts, it's carrying the weight of countless unknowns. Micrometeoroids smaller than a grain of sand can pierce through spacecraft like bullets. Solar flares can fry electronics mid-flight. Even the human body itself begins to unravel in zero gravity, muscles wasting away, bones dissolving as if the universe itself is rejecting our presence. And that's just the beginning. Today, we're pulling back the curtain on the 30 most shocking, overlooked, and downright bizarre dangers lurking in the cosmos. Some will sound like they're straight out of a horror movie, others are so subtle, you'd never see them coming until it's too late. But this isn't just about fear. It's about understanding the true cost of reaching for the stars, the sacrifices and the science that keep explorers alive in the most hostile environment imaginable. So buckle up. By the end of this journey, you'll never look at space the same way again. The first hidden danger in space might be invisible, but its effects are anything but. Cosmic radiation consists of high-energy particles, protons, atomic nuclei, even gamma rays barreling through the void at nearly the speed of light. Unlike Earth, where our atmosphere and magnetic field act as a protective shield, space offers no such luxury. Every astronaut venturing beyond low Earth orbit is bombarded by a relentless storm of these particles. Some come from our own sun during violent solar flares. Others originate from distant supernovas or black holes, carrying enough energy to punch straight through spacecraft hulls like they're made of paper. The damage isn't just theoretical. Back in 1989, a solar storm so powerful it caused blackouts across Quebec also sent radiation levels skyrocketing aboard the space shuttle Atlantis. Astronauts reported seeing flashes of light, their own retinas being struck by particles even with their eyes closed. Decades later, studies revealed Apollo astronauts who traveled to the moon faced radiation levels 200 times higher than on Earth, with long-term cancer risks that still aren't fully understood. Even today, the International Space Station, despite orbiting within Earth's protective magnetic field, requires heavily shielded storm shelters where crews retreat during solar eruptions. But it's not just human biology at risk. Electronics are equally vulnerable. In 2003, a single cosmic ray flipped a critical bit in the onboard computer of Japan's Adios 2 satellite, rendering its multi-million-dollar mission useless in an instant. Space agencies now spend fortunes radiation-hardening equipment, wrapping circuitry in layers of protective materials, yet breaches still happen. The deeper we venture into space toward Mars or beyond, the worse this invisible onslaught becomes. There's no quick fix, no magic material that blocks all radiation without adding impossible weight to spacecraft. It's a silent, omnipresent threat, forcing engineers and astronauts to walk a razor's edge between exploration and survival. Perhaps most chilling, we've only begun mapping radiation's long-term effects. unlike Earth-bound hazards, cosmic rays don't just cause surface-level damage. They shred DNA at the molecular level, triggering mutations that might take years or generations to fully manifest. Early studies suggest female astronauts face higher risks than their male counterparts, with reproductive systems particularly sensitive to radiation's ravages. Even shielded habitats on Mars would require astronauts to spend years underground during solar storms, turning the dream of colonization into a life spent hiding from the sky. Every mission plan, every hopeful blueprint for interplanetary travel, must first answer one grim question: how much radiation is too much before the stars become a death sentence? Floating in zero gravity might look like fun, no heavy lifting, effortless movement, the closest thing to flying humans will ever experience. But what happens when that weightlessness isn't just a few minutes on a roller coaster, but months or even years in space? The human body, evolved over millions of years to fight Earth's gravity, starts breaking down in ways that sound more like a medical horror story than science. Astronauts returning from long missions don't just wobble for a few days, they face permanent, sometimes crippling changes to their very biology. Take bones, for example. On Earth, your skeleton constantly rebuilds itself, cells breaking down old bone and replacing it with new, stronger material. But in microgravity, that process goes haywire. Without the stress of gravity, bones don't just weaken, they dissolve. Astronauts can lose up to 2% of their bone mass every month, the equivalent of decades of osteoporosis crammed into a single mission. Even after returning to Earth, some never fully recover. Russian cosmonaut Valery Polyakov, who spent a record 437 days aboard Mir, likened his legs to wet noodles for months, his muscles so atrophied he couldn't stand without assistance. Studies show some astronauts regain only 80% of their original bone density, meaning every long-duration mission is a gamble with irreversible damage. Then there's muscle. Without gravity's resistance, muscles, especially in the legs and back, wither at alarming rates. NASA found astronauts lose up to 20% of their muscle mass in just 5 to 11 days. That's why the International Space Station looks like a floating gym, packed with resistance machines and bungee cords. But even 2 hours of daily exercise can't fully stop the decay. Scott Kelly, after nearly a year in space, described his calves as flat as pancakes, his spine elongated by 2 inches, so much that his old clothes no longer fit. But the creepiest effects might be inside the skull. Prolonged microgravity shifts bodily fluids upward, increasing pressure on the brain and optic nerves. Over 40% of astronauts develop spaceflight-associated neuroocular syndrome, blurred vision, flattened eyeballs, even permanent retinal damage. Autopsies on mice flown in space revealed brain structure changes similar to traumatic injuries. And in 2018, MRIs showed astronauts' brains had literally shifted upward in their skulls, compressing against bone. Some still had these changes a full year after landing. Perhaps most unsettling, we still don't know the long-term consequences. Mars missions could last over 2 years, enough time for bones to become dangerously brittle, muscles to waste beyond repair, brains to reshape in ways we can't predict. Artificial gravity might help, but spinning habitats like sci-fi movies suggest brings motion sickness and engineering nightmares. For now, every astronaut boarding a spacecraft isn't just embarking on a mission. They're volunteering as test subjects in the largest uncontrolled medical experiment in history. The price of exploring the cosmos might not just be dollars or rocket fuel, but the slow, silent unraveling of the human body itself. Picture being trapped inside a metal can for 18 months, the same handful of faces every single day, no breeze on your skin, no sunlight that hasn't first passed through thick glass. Outside, an airless void stretches forever, no rescue possible, no quick return home. This isn't a dystopian novel. It's the reality astronauts face on long missions where psychological isolation becomes as deadly as any technical failure. Space doesn't just attack the body, it preys on the mind. History offers a grim preview. The Biosphere 2 experiment in the 90s sealed 8 people inside a self-contained habitat meant to mimic a space colony. Within months, oxygen levels dropped, food supplies dwindled, and the crew fractured into warring factions. One member began hoarding supplies, others stopped speaking entirely. Psychological evaluations later revealed plummeting morale, sleep disturbances, and cognitive decline, all without ever leaving Earth. Now imagine that same scenario playing out on Mars, where the nearest therapist is 40 million miles away, and a radio signal takes 20 minutes just to say, "Are you okay?" Even on the International Space Station, where astronauts rotate every 6 months, tension simmers beneath the surface. Small irritations, snoring, eating noises, personality clashes magnify in confinement. NASA psychologists now screen crews for compatibility like dating apps, but no algorithm can predict how isolation rewires the brain. Astronauts report space madness, sudden mood swings, irrational anger, even hallucinations from sensory deprivation. After months of canned air and recycled water, one astronaut described craving the smell of rain so badly he dreamed of thunderstorms for weeks, but the most insidious effect: time dilation. Without Earth's natural rhythms, days blending into weeks, no weekends, no seasons, the brain loses its anchor. Cosmonaut Valentin Lebedev, during a record-setting mission in the 80s, wrote in his diary about losing all sense of purpose. "You start to ask, why am I even here?" Modern studies show prolonged isolation shrinks the hippocampus, the brain's memory center, while cortisol levels skyrocket. Mars colonists wouldn't just battle loneliness, they'd wage war against their own biology, with no guarantee their minds would survive the journey intact. Solutions exist, but they sound like sci-fi. Virtual reality windows projecting Earth vistas, AI therapists programmed to detect depression in voice patterns. None have been tested for multi-year missions. Until then, every long-duration flight remains a gamble, not just on technology, but on the fragile human psyche itself. The void doesn't just kill with cold or radiation. It kills by making you forget what it means to be human. You're cruising peacefully in orbit, Earth spinning below like a blue marble, when suddenly a metallic flash streaks past your window closer than a bullet. That near miss wasn't a meteor. It was a shard of a shattered satellite, spinning at 17,500 miles per hour, 10 times faster than a rifle shot. And it's not alone. Right now, over 34,000 chunks of space debris larger than a softball are circling Earth like a cosmic minefield, with millions more too small to track. This isn't just clutter. It's an invisible hailstorm moving so fast, even a paint chip could punch through a spacesuit like a shotgun blast. The danger isn't hypothetical. In 1996, a French satellite was blindsided by debris from a rocket that had exploded a decade earlier. The impact packed the energy of a hand grenade, shredding the satellite's stabilizing boom. Then came 2009, when a defunct Russian satellite collided with an active American one over Siberia, creating over 2,000 new pieces of shrapnel, each now a bullet waiting to strike again. But the real nightmare scenario, Kessler Syndrome, named after NASA scientist Donald Kessler, it's a terrifying chain reaction where one collision spawns debris that triggers more collisions until low Earth orbit becomes an impassable junkyard. Think of it like a car crash on the highway, except every shattered piece of glass and metal becomes another car hurtling in random directions, causing infinite crashes. Within hours, critical satellites, GPS, weather monitoring, communications could be reduced to Swiss cheese. What makes this so insidious is speed. At orbital velocities, even a 1-centimeter screw carries the kinetic energy of a bowling ball dropped from a skyscraper. The International Space Station regularly dodges debris, its hull peppered with tiny craters from impacts. In 2021, a piece of space junk punched a hole clean through the station's robotic arm, missing vital components by sheer luck. Astronauts describe the sound of tiny impacts at night like grains of sand pinging off the hull. One strike in the wrong place, and that sound becomes the last thing they ever hear. Cleaning up this mess is like trying to catch bullets with a butterfly net. Proposed solutions sound like sci-fi. Giant nets, harpoons, even lasers to vaporize debris. But with over 3,000 dead satellites already in orbit plus fragments from anti-satellite weapon tests, the problem is accelerating faster than solutions. Every new SpaceX launch, every discarded rocket stage adds to the ticking time bomb above us. Unlike Earth's pollution, you can't see space junk with the naked eye. But make no mistake, we're building our own prison in the stars, one piece of floating shrapnel at a time. The next space age might not end with a grand mission to Mars, but with humanity trapped on Earth by a barrier of our own making. The moment an astronaut's boot sinks into the powdery surface of the Moon or Mars, an invisible killer kicks up around them, not radiation, not vacuum, but something far more insidious: dust. Not the harmless kind you brush off your shelf, but jagged, electrostatically charged particles finer than flour and sharper than broken glass. Apollo astronauts quickly learned this the hard way. After their moonwalks, they hauled sacks of gray powder back into the lunar module, only to find it clung to every surface like demonic glitter. Buzz Aldrin called it the most debilitating aspect of lunar surface activity. The crew of Apollo 17 suffered so badly from inhaled dust triggering fits of sneezing, watery eyes, and sore throats they nicknamed it lunar hay fever. And that was just a few days of exposure. What makes this dust so dangerous? Unlike Earth's weathered particles smoothed by wind and water, lunar and Martian dust is a product of eternal violence. Micrometeorite impacts fracture it into barbed, razor-edged shards. On the Moon, with no atmosphere to soften blows, these particles remain as sharp as the day they were shattered billions of years ago. Mars adds another nightmare: perchlorate salts woven into the dust, toxic enough to trigger thyroid damage if inhaled. Back in 2008, Phoenix lander experiments confirmed the soil was literally poison. One whiff could mean coughing fits turning into chronic bronchitis, then lung scarring, then cancer. NASA worst-case projections for a 500-day Mars mission suggest dust exposure could be as lethal as smoking a pack a day for decades. But the horror doesn't stop at lungs. Apollo missions proved this dust is viciously invasive. It jammed zippers, abraded helmet visors into frosted haze, and even short-circuited equipment. Imagine a Mars habitat's air filters clogging after weeks, forcing colonists to breathe toxic powder, or solar panels blanketed by dust storms, turning life support systems into ticking time bombs. The more we study it, the clearer it becomes. This isn't just dirt, it's an environmental weapon. Moon dust is so electrically charged it levitates, creeping into seals and joints like an intelligent adversary. Simulations show it could coat spacesuits so thoroughly that walking back indoors would drag pounds of carcinogens into living quarters with every step. Solutions sound like something from a mad scientist's lab. Magnetic airlocks to repel charged particles, ultrasonic vibrations to shake dust off suits. NASA experimented with all of them, but no fix is foolproof yet. The cruel irony: the very soil we'd mine for oxygen and water on Mars might be our undoing. Every scoop harvested could release clouds of poison. Future colonists won't just farm or build, they'll wage a daily war against the ground beneath their feet, where the line between resource and ruin is as thin as a speck of dust. One moment, your spacecraft is baking under the unfiltered fury of the sun, its metal skin scorching at 250 degrees Fahrenheit, hot enough to fry eggs on contact. The next moment, it slips into shadow and temperatures plummet to -250, colder than Antarctica's deepest ice. These aren't just numbers, they're a brutal reality that turns every spacecraft into a war zone of expansion and contraction, where materials scream under stress they were never designed to endure. Take the Parker Solar Probe, humanity's first mission to touch the Sun. Flying within 4 million miles of our star's surface, it faces temperatures that would vaporize most metals. NASA's solution: a revolutionary heat shield no thicker than a phone book, made of carbon composite so advanced it can withstand 2,500 degrees while keeping the spacecraft's instruments at room temperature. But here's the catch: the back of the probe, perpetually in shadow, is simultaneously freezing. One side is a blast furnace, the other a cryogenic nightmare, creating forces that could twist the craft apart like a piece of taffy. Engineers had to invent adhesives that wouldn't crack under the strain and joints that flex without failing, because in space there's no middle ground. You're either burning or freezing, often at the same time. This isn't just about solar missions. Every satellite, every Mars rover, even the International Space Station dances this thermal tango. Moon landers face a special hell: 14 days of relentless sunlight heating surfaces to 260 degrees, followed by 14 days of darkness plunging temperatures to -280. Metals expand and contract so violently that bolts loosen, seals degrade, and electronics fry. During Apollo 12, astronauts discovered their lunar module's exterior had warped from the temperature swings just hours after landing. The real terror: these swings aren't predictable. A satellite orbiting Earth might transition from sunlight to shadow dozens of times per hour, its structure flexing like a paperclip bent back and forth until it snaps. The Hubble Space Telescope's solar panels, for instance, suffered such severe thermal-induced vibrations that engineers had to develop entirely new damping systems mid-mission. Even mundane materials become enemies. Lubricants evaporate or turn to glue, batteries lose efficiency, and camera lenses fog or fracture from internal stresses. Solutions sound like something from alchemy: gold-coated mirrors to reflect heat, self-healing materials that seal their own cracks, even thermal cloaks designed to scatter extreme temperatures away from sensitive components. But for all our ingenuity, space remains the ultimate stress test, one where failure isn't just a setback, but a silent, freezing, or blistering death. Every spacecraft launched is a gamble against an environment that doesn't just resist us, it actively tries to tear our machines apart molecule by molecule. The silence of space isn't peaceful, it's predatory. One moment you're gazing at Earth's curvature through your helmet visor. The next, a malfunctioning seal triggers a hiss no one can hear. Within seconds, the vacuum outside becomes the enemy within. This isn't hypothetical. In 1971, the Soyuz 11 crew, Georgy Dobrovolsky, Vladislav Volkov, and Viktor Patsayev, learned this horror firsthand. Their capsule's ventilation valve burst open during re-entry, exposing them to near-total vacuum. By the time recovery teams pried open the hatch, all three were dead, their faces dotted with hemorrhages from capillaries that had ruptured outward. Autopsies revealed the truth: space doesn't just suffocate you, it dismantles you from the inside out. Embolism is the first nightmare. At zero pressure, bodily fluids no longer obey gravity or biology. Saliva boils at body temperature. Blood vessels swell like overfilled balloons as nitrogen bubbles form in your bloodstream, a condition divers call the bends, but accelerated to lethal speed. Your skin bloats to twice its size, not from water, but from vaporizing moisture forcing itself between tissue layers. Eyes become useless as corneas dehydrate into cloudy film. And yet, consciousness persists for those first terrifying seconds. Soviet experiments with accidentally exposed dogs showed victims remained awake for up to 90 seconds, long enough to feel their own bodies turning against them. Then comes hypoxia. Unlike drowning or choking, where panic stems from air hunger, vacuum-induced oxygen starvation is eerily quiet. Your lungs empty in one brutal exhale, but without pressure they can't refill. No gasp, no scream, just a dizzying fade as brain cells starve. NASA research suggests you'd pass out in 15 seconds, but not before frostbite like ice crystals formed in your mouth and nose from evaporating moisture. The worst part, some of it's survivable if rescue comes fast. In 1965, a NASA test subject's pressure suit failed in a vacuum chamber. He blacked out but revived moments later when technicians repressurized the room. His last memory, the spit on his tongue bubbling like boiling water. Spacesuits are miracles of engineering for a reason. Modern designs include redundant pressure layers, automatic sealants that clot small tears, and helmets with emergency oxygen reserves. But all it takes is one micrometeorite strike in the wrong place, one overlooked manufacturing flaw, and the void comes rushing in. Astronauts train for this scenario like soldiers drilling for ambushes, quickly locating and sealing leaks before their own breath becomes toxic. Because in space, death isn't always an explosion or a fire. Sometimes it's just a whisper of air escaping into the infinite, and the terrible knowledge that no one can hear you scream. Imagine shouting for help and waiting 40 minutes just to hear a reply. Now picture that delay happening during a life or death crisis millions of miles from home. That's the chilling reality astronauts bound for Mars will face, where messages take anywhere from 4 to 24 minutes to travel between planets depending on their orbits. Unlike the Apollo missions, where mission control could troubleshoot in real time, like the frantic improvisation that saved Apollo 13, future crews will be utterly, terrifyingly alone when seconds count. The Apollo 13 disaster showed us the power of instant communication. When an oxygen tank exploded 200,000 miles from Earth, Jim Lovell's famous words, "Houston, we've had a problem," triggered an immediate response. Engineers scrambled to design a carbon dioxide scrubber workaround using only the materials on hand, relaying step-by-step instructions while the crew fought for survival. That same emergency on Mars, the crew would radio for help, then wait 40 agonizing minutes just to hear, "Say again, we missed that last part." By the time Earth grasps the situation and suggests a solution, 90 minutes could pass. 90 minutes with a failing oxygen system, a medical emergency, or a fire spreading through the habitat. But delays aren't just about emergencies. Routine operations become logistical nightmares. A simple request, "Should we drill here?" turns into a half-day debate. Navigation corrections, software glitches, even medical diagnoses all require agonizing pauses. During NASA Mars rover missions, scientists joke about Mars time, where each day's commands are uploaded blindly based on yesterday's data. For humans, that lag could mean planting a flag in toxic soil, taking a wrong step off a cliff, or misreading a radiation alert, all before Earth even knows there's a problem. The psychological toll might be worse. Studies in Antarctica, where winter isolation mimics spaceflight, show even 2-second delays in satellite calls fray nerves. Now stretch that to 20 minutes of strained small talk, missed jokes, and birthdays where loved ones' voices arrive hours after the celebration ended. The first Mars colonists won't just be explorers, they'll be the most isolated humans in history, living with a loneliness deeper than any astronaut has ever known. Solutions sound borderline absurd. AI co-pilots making split-second decisions, pre-recorded emergency holograms, none eliminate the core truth. Mars missions will be the first time humanity ventures beyond the safety net of real-time contact. Every decision, every crisis, every whispered fear will echo into the void unanswered. The Red Planet isn't just a test of engineering, it's a test of whether humans can endure being truly, utterly cut off from home. The sun isn't just a source of light and warmth, It's a sleeping giant capable of unleashing storms violent enough to knock humanity back to the Dark Ages. Coronal mass ejections, or CME, are the Sun's deadliest tantrums, billion-ton eruptions of magnetized plasma hurtling through space at millions of miles per hour. When one of these monsters hits Earth, the results aren't just pretty auroras, they're catastrophic surges of energy that can melt power grids, cripple satellites, and turn unshielded astronauts into walking radiation experiments. Take March 13, 1989. A CME slammed into Earth's magnetic field with the force of a nuclear warhead. No explosion, no fireball, just an invisible tsunami of charged particles. Within 90 seconds, Quebec's entire power grid collapsed. 6 million people sat in darkness as transformers exploded like popcorn, some so badly damaged they had to be replaced by helicopters. Meanwhile, 250 miles up, the Space Shuttle Discovery found itself swimming through a sea of radiation. Astronauts reported blinding flashes in their eyes, cosmic rays tearing through their optic nerves like microscopic bullets. Even today, the International Space Station's crew ducks into shielded compartments during solar storms, knowing their delicate electronics and DNA are under siege. But the real nightmare, a Carrington-level event. In 1859, a solar storm so powerful it set telegraph offices on fire and painted the skies crimson as far south as Cuba. If that happened today, experts estimate global blackouts could last years with trillions in damages. Satellites would drop from orbit like flies, GPS would fail, and modern aviation reliant on electronics would grind to a halt. For Mars missions, it's even worse. Without Earth's magnetic field as a buffer, astronauts caught outside their habitat during a CME would absorb a lifetime's worth of radiation in hours. NASA worst-case simulations show solar protons shredding bone marrow so badly, victims would need emergency blood transfusions just to stay alive. The cruel irony. We see these storms coming but can't always stop the damage. Solar observatories like SOHO give us about 48 hours warning, enough to power down critical systems on Earth. But spacecraft, they're sitting ducks. In 2022, SpaceX lost 40 brand new Starlink satellites to a minor solar storm, their delicate electronics fried before they even reached orbit. Future lunar or Martian bases will need underground storm shelters lined with water or lead literal bunkers against the sun's fury, because in space, good weather isn't just about clear skies. It's about surviving the invisible firestorms that can cook you alive from 93 million miles away. We spend so much time worrying about space killing us, but what if we're the invaders? Every rocket launch doesn't just carry astronauts or rovers, it carries trillions of tiny hitchhikers, bacteria from Earth clinging to circuit boards, hiding in air vents, nestled into the creases of spacesuits. These microbes have survived extreme radiation, boiling acids, even the vacuum of space in lab tests, and if they make it to another world, they could annihilate alien life before we even discover it. Or worse, trick us into thinking we've found extraterrestrials when all we've really found are our own germs mutated beyond recognition. This nightmare scenario has a name: forward contamination. When Viking landers touched down on Mars in 1976, they'd been baked at 250 degrees Fahrenheit for over 30 hours. NASA attempt to sterilize them. But modern DNA sequencing reveals how woefully inadequate that was. Scientists recently discovered bacteria living inside the clean rooms where spacecraft are assembled, organisms like Tersicoccus phonesis, resistant to alcohol, ultraviolet light, and peroxide treatments meant to kill them. Some microbes, like Deinococcus radiodurans, can survive doses of radiation 5,000 times stronger than what would kill a human. These aren't just contaminants, they're biological extremists waiting to colonize new worlds. The stakes are astronomical. Imagine landing on Europa, Jupiter's ice-covered moon, drilling into its hidden ocean only to realize that alien microbes in your samples are just Earth's common pseudomonas that hitched a ride years ago. Or worse, Martian soil tests positive for life, but further study reveals it's actually terrestrial bacteria that evolved rapidly in the harsh environment. NASA's Planetary Protection Office exists solely to prevent this, enforcing sterilization protocols so strict they'd make a pharmaceutical factory blush. Mars rovers like Curiosity are built in ISO Class 100 cleanrooms where fewer than 100 particles float in a cubic meter of air. Engineers swab every surface with cotton buds, culturing bacteria to hunt down persistent stowaways. Yet leaks still happen. In 2019, an Israeli lunar lander crashed on the moon carrying thousands of dehydrated tardigrades, microscopic water bears capable of surviving space vacuum. They weren't supposed to be there. A commercial company had secretly added them as part of an archive project, bypassing planetary protection rules entirely. The terrifying truth: we're terrible at playing God with biology. Microbes have been found thriving inside nuclear reactors, Antarctic ice cores, even the outer hull of the International Space Station. No amount of bleach or radiation guarantees sterilization because life, it turns out, is far more tenacious than our protocols. The ethical dilemma cuts deep. How sterilized is sterilized enough? Viking-level baking would destroy modern electronics. Some propose dousing spacecraft in plasma or zapping them with electron beams, but each method risks damaging sensitive instruments. Meanwhile, private companies like SpaceX operate under looser guidelines, prioritizing speed over caution. With human missions to Mars looming, the risk skyrockets literally. An astronaut's gut bacteria alone carries over 1,000 species. One leaky spacesuit seal, one unsterilized tool dropped in the dust, and we might inadvertently plant Earth's flag on another world in the worst way possible, not with a plaque or a footprint, but with a bacterial smear that outlasts all our monuments. Perhaps the greatest irony: in our quest to discover alien life, we might become the invasive species ourselves, spreading Earth's organisms like cosmic graffiti, while desperately scrubbing our spacecraft to prevent exactly that catastrophe. The universe's first contact story could be less "hello from another world" and more "oops, we brought our germs." We've spent decades sterilizing our spacecraft to protect other worlds from Earth's microbes, but what if the real danger isn't what we're taking up there, but what we might bring back? The Apollo 11 crew didn't just return with moon rocks in 1969, they returned with a mystery. Were those gray samples sterile dust, or could they harbor something alien? NASA quarantined Armstrong, Aldrin, and Collins like biohazards for 3 weeks, sealing them in a converted Airstream trailer with glovebox labs. Scientists even injected lunar material into mice, watching for signs of infection. All tests came back clean, but the fear never fully faded because backward contamination isn't science fiction. It's a silent threat that could turn every sample return mission into a potential pandemic starter. Modern experts warn that Martian microbes, if they exist, might not play by Earth's biological rules. Our immune systems evolved to fight terrestrial pathogens, not organisms shaped by a completely different evolutionary path. Dr. Carl Sagan once compared it to Europeans arriving in the Americas, except this time, the natives are microscopic and potentially far deadlier, the scariest possibility. A scenario called oblique pathogenesis, where Martian life doesn't infect us directly, but hijacks Earth's existing bacteria like a puppet master. Imagine a virus-like entity from Mars reprogramming E. coli in your gut to produce toxins, or worse, merging with terrestrial microbes to create hybrid horrors. That's why Mars sample return missions are the ultimate high-stakes treasure hunt. NASA Perseverance rover is currently sealing tubes of Martian soil with surgical precision, but the real challenge comes when those samples hurtle back to Earth in the 2030s. The proposed containment protocol reads like a bioweapon lab's checklist: robotic transfer arms, multiple airlocks, ultraviolet decontamination chambers, and fail-safes that could incinerate the entire payload if breached. Even the landing site might be an abandoned island or a floating platform anywhere but near human populations, yet skeptics argue we're overreacting. After all, Martian meteorites land on Earth regularly, over 500 pounds of them scattered across Antarctica and deserts. If Mars harbored voracious microbes, wouldn't they have invaded by now? But NASA counters that meteorites are sterilized by fiery entry, while carefully curated samples could preserve organisms shielded inside protective rock layers. The debate splits scientists. Some call for airtight biosafety level 4 labs, while others accuse NASA of paranoia that could delay discovery for decades. History offers a chilling parallel. When researchers opened King Tut's tomb in 1922, rumors spread of a mummy's curse killing those who disturbed it. Most dismissed it as superstition until modern analysis revealed ancient spores of toxic mold in the burial chamber, possibly inhaled by the excavators. Now imagine that scenario playing out with a pathogen no human immune system has ever encountered. The Apollo quarantine might have seemed excessive at the time, but it set a precedent. Space exploration isn't just about what we find out there, it's about making sure it doesn't find us. Imagine cracking open a months-old food package on the International Space Station, only to be hit with the rancid stench of spoiled meat, while floating 250 miles above Earth with no grocery store in sight. Space cuisine isn't just about taste, it's a high-stakes battle against invisible forces that turn meals into toxic hazards. Cosmic rays, the same particles that threaten astronauts' DNA, also wage war on their food supply. These high-energy photons smash into vitamins and proteins, breaking them apart at the molecular level. Studies show vital nutrients like vitamin C and folate degrade twice as fast in space as on Earth. That fresh orange juice pouch, after 6 months in orbit, it might as well be colored water, but radiation's only half the problem. Closed-loop systems like the ISS are mold paradise, warm, humid, and packed with organic material. In 2016, astronauts discovered an entire batch of Russian space bread speckled with greenish-black patches. Cameras later revealed fungal spores lurking in air vents, thriving despite rigorous cleaning. The culprit, Penicillium rubens, a common mold strain, turned super resilient in microgravity. Without gravity to anchor them, spores float endlessly instead of settling, colonizing every crevice like invisible invaders. NASA microbiologists were stunned to find fungi growing on materials once deemed inhospitable: acrylic glass, aluminum, even the adhesive used for station repairs. The consequences go beyond gross meals. Some space molds produce mycotoxins, poisonous compounds that trigger everything from nausea to liver damage. In 2018, astronauts reported mysterious headaches and dizziness later traced to aspergillus contamination in the life support system. The solution? A brutal triage. Crews regularly jettison entire food shipments through the airlock, watching millions in supplies burn up in the atmosphere rather than risk poisoning. Footage shows floating bags of rancid cheese and bloated meat cans spiraling toward Earth, a surreal grocery run in reverse. Future Mars missions face an even grimmer equation. With resupply impossible, colonists could starve if radiation and mold wipe out their provisions. NASA are working on solutions that sound like sci-fi. Vitamin-fortified edible films, 3D printed meals with built-in antimicrobials, even gene-edited crops resistant to cosmic degradation. But for now, every bite in space is a gamble, a race against time where the loser gets a mouthful of moldy, nutrient-dead rations. The real irony: in trying to conquer the final frontier, we might be outsmarted by the same microbes that plague our bread bins back home. You'd think floating in zero gravity would feel like lying on the perfect mattress, no pressure points, no tossing and turning. But astronauts rarely sleep more than 6 hours a night, trapped in a relentless cycle of exhaustion that turns simple tasks into potential disasters. The International Space Station isn't just a laboratory, it's one of the noisiest places humans have ever tried to sleep, with cooling fans, pumps, and machinery humming at 72 decibels around the clock. That's louder than a vacuum cleaner running non-stop. Crews wear earplugs, but sound travels through structures in space, vibrating through bones like a never-ending dental drill. Add the stress of 16 sunrises and sunsets every 24 hours, throwing circadian rhythms into chaos, and you've got a recipe for chronic fatigue that's nearly impossible to escape. The consequences aren't just bleary eyes. Sleep deprivation played a hidden role in one of spaceflight's darkest moments. Before the Challenger disaster in 1986, engineers at Morton Thiokol had worked 36 hours straight debating whether to launch in freezing temperatures. Exhausted and pressured by NASA, they reluctantly approved, overlooking critical O-ring data that might have stopped the tragedy. The Rogers Commission later cited fatigue as a key factor in the flawed decision-making chain. Fast forward to today, and NASA studies show sleep-deprived astronauts make 50% more mistakes during simulations, with reaction times matching someone legally drunk. In a world where a single typo could mean missing a re-entry window or miscalculating oxygen levels, that's not just dangerous, it's potentially fatal. Modern missions try everything from melatonin to strict light therapy, but solutions often create new problems. Sleeping pills are risky in emergencies, and those famous vertical sleep pods. Many astronauts report waking up disoriented, arms floating freakishly in the darkness. Some resort to Velcro-ing themselves to walls, only to be jolted awake by emergency alarms or docking maneuvers. Russian cosmonaut Valery Polyakov, who spent 14 straight months on Mir, described the toll. You stop dreaming of Earth, you stop dreaming at all. Brain scans reveal spacefarers lose up to 80% of REM sleep, the phase crucial for memory and emotional regulation, leaving them in a perpetual fog. Mars poses an even grimmer equation. With communication delays making shift work impossible, crews will need perfect synchronization. But studies in Antarctic isolation show small groups naturally fracture into mismatched sleep cycles, breeding irritability and errors. Proposed solutions sound dystopian. AI sleep coaches monitoring brainwaves, LED ceilings mimicking Earth's day-night cycle, even electrical stimulation to force neural recovery. Yet the core problem remains unchanged. Space isn't just hostile to our bodies. It's waging war on the very thing that makes us human, our need to close our eyes, drift away, and wake up ready to face the day. Until we solve that, every mission is one sleepless night away from catastrophe. Fire doesn't behave the way you'd expect in space. There's no up for heat to rise, no convection currents to carry flames. Instead, fire becomes a creeping, insidious predator, spreading in every direction at once like a living thing. This nightmare became horrifically real aboard Russia's Mir space station in 1997 when an oxygen-generating canister burst into flames. Within seconds, the crew found themselves trapped with a fireball that burned at 2,000 degrees Fahrenheit, spewing molten metal globules that floated eerily through the cabin. Thick, toxic smoke quickly filled the station, smoke that doesn't dissipate in microgravity, but forms suffocating clouds around your head. Astronaut Jerry Leininger later described the terror of watching fire explode outward in all directions, the flames licking at wiring and equipment just inches from their faces. The crew fought it with fire extinguishers for 14 agonizing minutes before it burned itself out. But not before the blaze nearly breached Mir's hull, which would have turned the entire station into a tomb. What makes fire so deadly in zero gravity? Flames form strange blue orbs instead of the teardrop shapes we know on Earth. Without gravity pulling cooler air downward, oxygen doesn't replenish at the flame's base, creating bizarre, spherical fires that burn at lower temperatures but are far harder to extinguish. NASA's flame extinguishment experiment aboard the ISS revealed something even scarier. Some materials that would self-extinguish on Earth, like certain fabrics or wire insulation, keep burning indefinitely in space, smoldering like ghostly apparitions until every last fuel source is consumed. Footage from these tests shows a single spark igniting a strip of silicone, which then creeps along like a glowing snake, leaving a trail of molten debris that could float into sensitive equipment or an astronaut's lungs. The solutions sound like something from a firefighter's worst nightmare. Traditional extinguishers are useless. Spraying liquid just creates floating, flammable droplets. Modern spacecraft use CO2 systems, but even these have limits. During a 2016 test, NASA intentionally lit a massive fire inside an unmanned Cygnus cargo ship after it left the ISS. Cameras showed the flames spreading in unpredictable pulses, at times seeming to pause before suddenly surging forward, the most chilling discovery. Some materials burned faster in space than on Earth, defying all conventional fire science. Future Mars habitats may need embedded fire suppression grids, think of sprinkler systems, but with fog-like water mists designed to envelop floating fireballs without shorting out electronics. Perhaps the most unsettling truth is how little we still understand. A single electrical short, an overheated battery, or even static discharge could trigger a disaster no amount of training can fully prepare for. Fire on Earth obeys rules, fire in space follows none. And until we crack its alien physics, every spacecraft remains one spark away from becoming a floating crematorium. That clear water floating in an astronaut's drink pouch might look pristine, but its journey to their lips is anything but pure. Every drop aboard the International Space Station has been recycled, sometimes multiple times, through a system that turns yesterday's coffee, sweat, and even urine into tomorrow's drinking water. It's a technological marvel until it becomes a biological nightmare. The process starts with what NASA politely calls water recovery. Urine gets funneled into a distiller that spins at high speed, forcing liquids through a filtration membrane while leaving behind a thick, briny sludge. Next, the purified water gets zapped with ultraviolet light and filtered through catalytic reactors to break down any remaining contaminants. The result: water so clean it surpasses most earthly tap water standards. Crew members joke that today's urine is tomorrow's espresso, but the system's fragility is no laughing matter. Apollo 13's near disaster showed just how quickly life support can unravel. While their oxygen crisis stole headlines, the crew also faced a hidden water emergency. With power crippled, they couldn't run the command module's purification system, forcing them to ration drops from the lunar lander's limited supply. At one point, they went nearly 40 hours without drinking, dehydration so severe mission control worried they'd pass out during re-entry. Modern systems are more robust, but failures still happen. In 2009, the ISS's urine processor suddenly shut down, spewing a pungent mix of half-treated waste into the cabin. Engineers later discovered calcium buildup from astronaut diets had clogged the works like arterial plaque, requiring a literal vinegar flush to dissolve the blockage. The real horror isn't just malfunction, it's what lurks in those filters when they fail. Microbiologists found ISS water processors harboring biofilms of Ralstonia picketii, a bacterium that thrives in purified water and causes respiratory infections. Others discovered fungus colonies so dense they resembled wet moss, releasing musty odors that clung to every sip. NASA now monitors the system with DNA scanners, hunting for pathogens that might slip through the purification maze. Future Mars missions will push recycling to terrifying extremes. With no resupply possible, every milliliter must be reclaimed, including moisture from breath and sweat. Prototype systems extract water from fecal matter, yielding a clear liquid politely termed distillate. Early testers described the flavor as metallic, with an aftertaste no amount of coffee powder could mask. One engineer involved in the project put it bluntly: "You're basically drinking yesterday's bathroom break with extra steps, yet the alternative is worse." Lose water recycling on a Mars mission, and you're looking at death by thirst within days, a grim calculus that turns every flush into a life or death equation. The real danger isn't the Ike factor. It's the razor-thin margin between survival and catastrophe, where one faulty valve could leave you choosing between drinking from the backup toilet or suffocating in your own waste. Rocket fuel isn't just explosive, it's a slow-acting poison that can kill you long after the engines shut down. Hydrazine, the toxic cocktail powering most spacecraft thrusters, smells faintly of ammonia but carries a punch far deadlier. A single drop on bare skin triggers chemical burns that eat through tissue like acid. Inhale just 30 parts per million, about one whiff from a leaking valve, and your lungs start filling with fluid, drowning you from the inside out. This isn't hypothetical. During a routine test in 1981, a NASA technician accidentally exposed himself to hydrazine vapors. Within hours, his organs began failing. Doctors pumped his stomach and flooded his system with antidotes, but the damage was irreversible. He slipped into a coma and died 2 weeks later, his autopsy revealing liver and kidneys turned necrotic as if dissolved by invisible fire. The horror compounds when leaks happen mid-flight. Spacecraft carry hundreds of pounds of hydrazine in pressurized tanks, often routed through aging pipes mere inches from crew compartments. In 1975, the Apollo-Soyuz mission nearly ended in disaster when toxic fumes seeped into the cabin during re-entry. Astronauts described a creeping dizziness, their vision tunneling as the gas mixed with their air supply. Only frantic mask adjustments prevented tragedy. Decades later, shuttle crews reported finding eerie yellow stains around fuel lines, a telltale crystallized hydrazine residue that could turn gaseous with the slightest vibration. NASA contingency protocol for such leaks reads like a horror script. Seal off affected modules, don gas masks, and pray the ventilation system purges the poison before it purges you. But the most catastrophic demonstration of hydrazine's lethality came not in space but on the launch pad. On October 24, 1960, the Soviet Union's Netherlands catastrophe unfolded with brutal efficiency. A prototype R-16 missile, fueled with over 120 tons of hydrazine-based propellant, suffered a pre-launch electrical fault. Engineers rushed to fix it, disregarding safety protocols. Then, whether from a stray signal or static spark, the second-stage engines ignited prematurely. The explosion wasn't just fire and shock waves, it was a hydrazine-fed inferno. Flames reaching 2,000 degrees Celsius instantly vaporized technicians near the pad. Others farther away suffered slower agony as toxic clouds rolled over them, melting lungs into spongy masses. Officially, 78 perished, though insiders claim the true toll exceeded 120. Survivors described victims running like torches before collapsing, their uniforms still burning even as their organs shut down from systemic poisoning. The incident was so horrific Moscow suppressed all details for 30 years, leaving only charred photographs and whispered accounts. Modern safety measures have reduced but not eliminated the risks. SpaceX's Crew Dragon uses safer propellants for its abort system, while NASA experiments with green alternatives like hydroxylammonium nitrate. Yet hydrazine persists in satellites and deep space probes, its ruthless efficiency outweighing its dangers. Cleanup crews at launch sites still wear silvered suits resembling nuclear gear, knowing one pinhole leak could mean death. The cruel paradox, this same toxin that threatens astronauts also enables their survival, powering the thrusters that keep them on course or dodge space debris at critical moments. Every fiery liftoff isn't just a triumph of engineering, it's a pact with a chemical executioner, where the margin between mobility and mortality is as thin as a fuel line's weld. Spinning a spacecraft to create artificial gravity sounds like the perfect solution to muscle wasting and bone loss, until you actually try it. That iconic scene from 2001, a space odyssey with astronauts jogging effortlessly around a glowing centrifuge, glosses over the brutal reality. Spinning habitats aren't just engineering headaches, they're vomit-inducing death traps waiting to happen. The human inner ear, evolved over millions of years to handle Earth's steady gravity, goes into full revolt when subjected to rotational forces. Even slow spins trigger something called Coriolis sickness, a dizziness so severe it makes standard space nausea feel like a mild hiccup. Tilt your head too fast in a rotating habitat and your brain receives conflicting signals. Your eyes see movement, but your inner ear screams that you're tumbling through space. The result: violent vertigo, cold sweats, and an unstoppable urge to empty your stomach in zero gravity, a biohazard nightmare waiting to happen. NASA early experiments with rotating rooms in the 1960s revealed just how bad it gets. Test subjects strapped into spinning chairs couldn't last 10 minutes without debilitating dizziness. Some reported symptoms lasting days after just brief exposure, their balance so shattered they couldn't walk straight. Modern studies show even gradual rotations like a Mars-bound ship spinning at 3 revolutions per minute cause 60% of people to vomit within an hour. For long-term habitats, that's not just uncomfortable, it's mission-critical. An astronaut puking during a fire drill or medical emergency could mean choking to death in their own helmet. Then there's the engineering nightmare. To mimic Earth's gravity, a spacecraft would need to be enormous. Picture a wheel over 200 meters wide spinning at a gentle pace. Build it too small, and the spin creates a gravity gradient so extreme your feet feel twice as heavy as your head, turning every step into a slog through quicksand. Early designs for NASA's Nautilus X concept involved inflatable modules dangling from cables like a high-stakes circus act, until engineers realized a single micrometeorite strike could turn the whole thing into a spiraling wreck. Even the International Space Station's centrifuge accommodation module, a pet project in the 2000s, was scrapped when vibrations threatened to shake the entire station apart. The cruel twist: spin gravity might be too effective. Studies in centrifuges show prolonged exposure to even partial gravity could trigger new problems, like blood pooling dangerously in the legs or spinal discs expanding unevenly after months in microgravity. A Mars crew might spend their entire 6-month transfer ride fighting nausea in a spinning ship, only to collapse on arrival because their bodies forgot how to handle full gravity. Proposed workarounds sound like torture devices: spinning sleeping pods that only activate at night, or staggered rotations that slowly acclimate crews. Techniques that might reduce sickness but would turn daily life into a never-ending amusement park ride from hell. Science fiction makes artificial gravity look effortless. Reality paints a far messier picture, one where the cure for space's ravages might be worse than the disease. Until we crack the code on spinning habitats without turning astronauts into human gyroscopes, every deep space mission remains a choice between floating to death or spinning straight into misery. Einstein's theory of relativity isn't just abstract physics. It's a silent thief stealing time from astronauts who venture too far from home. Every second spent cruising toward Mars at tens of thousands of miles per hour chips away at their connection to Earth in ways that feel ripped from a sci-fi thriller. Thanks to time dilation, the faster you travel through space, the slower your clock ticks compared to those left behind. On a Mars mission spanning 2.5 years, astronauts might return to find Earth has aged an extra fraction of a second. Sounds negligible until you realize these microseconds snowball over multiple trips, leaving interplanetary travelers out of sync with everyone they've ever known. The movie Interstellar exaggerated this effect for drama, where hours on a waterlogged planet equaled decades back home, but the science behind it is unnervingly real. GPS satellites orbiting Earth experience it daily. Their atomic clocks tick faster than ground-based ones by about 38 microseconds per day. Engineers have to correct for this, or your phone's map app would steer you into fields within minutes. Now scale that up to a Mars-bound ship traveling at 15,000 miles per hour for months. Calculations show astronauts making 5 round trips could return to find Earth's calendar nearly 2 seconds ahead of theirs. Over centuries of colonization, entire generations might diverge. Imagine a Martian great-grandparent video calling their Earth-bound descendants only to find the family line has aged decades faster. The psychological toll could be profound. Time dilation isn't just about clocks, it's about shared experiences slipping out of alignment. A Mars settler watching Earth's live broadcasts would see events unfold slightly after they happened, like living in a delayed echo. Negotiations between planets would require literal time checks to sync legal contracts or trade agreements. Even simple birthday messages from Earth could arrive late, their celebratory meaning diluted by the void's indifference to human milestones. But here's the twist: time dilation isn't the only thief. The vast distances between planets introduce communication delays that fracture time just as brutally. A couple arguing over a Mars-Earth video link would face 20-minute pauses between screams and apologies, turning every spat into a glacial ordeal. The ultimate irony: in trying to conquer space, we might end up prisoners of time, forever chasing a present that's already slipped through our fingers. Out in the void between planets, there's no such thing as a harmless speck of dust. A grain of sand drifting past your window isn't drifting at all. It's screaming toward you at over 36,000 miles per hour, packing the kinetic punch of a .50 caliber bullet. These aren't just meteoroids, they're cosmic shrapnel, remnants of ancient asteroid collisions and comet tails, invisible until they strike. And strike they do. NASA records over 100 tiny impacts on the International Space Station every year, each one a potential catastrophe waiting to happen. The noise alone chills astronauts to the bone. Audio captured inside the ISS reveals eerie metallic pings at all hours, like hail hitting a tin roof, except each tap represents an object moving 10 times faster than a sniper round. In 2021, one such impact punched a clean hole through the station's Canadian-built robotic arm, leaving a jagged crater in its wake. Cameras later identified the culprit, a fleck of space debris no larger than a pencil tip. Engineers breathed a sigh of relief. Had that same projectile struck a module's hull, the resulting air leak could have forced an emergency evacuation. But the real terror lies in what we can't track. Ground radar spots objects down to 5 centimeters in low Earth orbit, but most micrometeoroids are far smaller. The Apollo missions faced this first, and their command modules returned pockmarked with microscopic craters, some barely visible to the naked eye. Analysis revealed these weren't gentle brushes. Hypervelocity impacts vaporize material on contact, blasting out superheated plasma that etches glass and melts metal. Modern spacecraft wear Whipple shields, multi-layered armor with outer sheets designed to shatter incoming projectiles, dispersing their energy before they reach the pressurized hull. Yet some near misses defy even the best defenses. In 1983, the Space Shuttle Challenger's windshield took a direct hit from a fleck of paint. The resulting crater was so deep, engineers worried a second strike in the same spot could crack it open like an eggshell. Decades later, ESA's Copernicus Sentinel-1, a satellite, was blindsided by a millimeter-wide particle, likely a stray bolt fragment, that drilled a 40-centimeter hole through its solar panel. The impact released enough energy to briefly destabilize the satellite's orbit, as if it had been kicked by an invisible giant. Mars missions will face even deadlier odds. Beyond Earth's protective magnetosphere, spacecraft endure a constant sandblasting from interplanetary dust. NASA's Juno probe en route to Jupiter logged over 600 strikes per day during its crossing of the asteroid belt. Future colonists might wake to find their habitat walls peppered with microscopic entry wounds, each one a silent testament to the universe's indifference. The cruel irony: these aren't rare anomalies. Every minute of every day, your body is being bombarded by similar particles in Earth's atmosphere. You just never feel them because our planet's thick air vaporizes them into harmless streaks of light we call shooting stars. In space, there's no atmosphere to play shield. Every meteoroid, no matter how small, arrives with murderous intent. So why haven't we lost more spacecraft to these invisible bullets? Part luck, part obsessive preparation, ISS crews conduct regular leak drills, training to seal off modules within minutes. Lunar-bound Artemis missions will carry emergency patch kits filled with space-grade epoxy. Think interstellar duct tape. But the ultimate solution might lie in deflection. Experimental dust detectors using lasers or electrostatic fields could one day act like early warning systems, giving crews precious seconds to rotate vulnerable equipment away from incoming fire. Until then, every mission remains a high-stakes game of dodgeball, where the balls are smaller than a grain of rice and move faster than any human reflex. The promise of 3D printing in space sounds like a futuristic dream. Need a wrench, print it. Lose a bone to zero gravity decay, grow a new one. But the reality unfolding aboard the International Space Station reveals a far messier truth, where radiation, microgravity, and the cruel laws of fluid dynamics conspire to turn cutting-edge tech into a high-stakes gamble. Take the wrench. NASA famously emailed to the ISS in 2014, heralded as a milestone for off-world manufacturing, what they didn't broadcast. That same wrench snapped under minimal torque 6 weeks later, its layers delaminating like stale pastry. Autopsies showed the culprit wasn't design flaws, it was space itself. Printing in microgravity defies every assumption that works on Earth. Molten polymers don't drip obediently through nozzles. They coil and cling like spider silk, creating weak points between layers. Metals sintered in orbital furnaces cool unevenly, leaving microscopic voids that turn tools into fragile replicas. Even the ISS's carefully calibrated printers require constant tweaking, adjusting for thermal warping as the station swings from blistering sunlight to cryogenic shadow every 45 minutes. Footage from a 2018 experiment shows a titanium bracket curling upward like a dried leaf mid-print, ruined by temperature swings no Earth-bound engineer would ever face. But the real horror show begins when you swap tools for tissues. Bioprinting organs in space, a concept floated by labs hoping to leverage microgravity's gentle embrace, collides with an invisible enemy, cosmic rays shredding living cells at the molecular level. Russian experiments on the ISS exposed bioinks to 6 months of orbital radiation, only to find the printed cardiac tissues riddled with DNA fractures. The samples that survived looked healthy under microscopes until stimulated, when they spasmed erratically like malfunctioning engines. NASA Advanced Plant Habitat witnessed similar chaos. Soybean roots printed in orbit grew sideways through their own vascular systems, their cellular guidance systems scrambled by particle bombardment. Solutions sound equal parts ingenious and desperate. Some propose magnetized nozzles to control swirling polymers or arc furnaces that melt metals uniformly in 0G. Bioprinting advocates suggest embedding stem cells with radiation-resistant tardigrade proteins, but each fix introduces new nightmares: magnetic fields interfering with navigation systems or transgenic tissues triggering immune revolts. The wrench that failed had been printed as a simple test. The stakes skyrocket when you're printing a trachea for an astronaut choking on lunar dust or a valve for a failing Mars habitat air system. Every layer printed in space isn't just a technical challenge, it's a bet against physics itself, where the house always wins. Picture a lunar mining outpost in 2040, its robotic drills extracting precious helium-3 for fusion reactors back on Earth. Suddenly, a rival nation's lander touches down mere meters away, claiming the same crater under a safety buffer zone clause in their corporate charter. No shots fired, no borders crossed, just a tense standoff where Earth's laws carry no weight. This isn't sci-fi paranoia. It's the legal black hole left by the 1967 Outer Space Treaty, a well-intentioned but dangerously vague document that declares celestial bodies the province of all mankind, while offering zero enforcement mechanisms. The treaty bans nuclear weapons in orbit but says nothing about kinetic rods dropped from space, silent, city-leveling projectiles that could strike with the force of a nuke without technically violating the agreement. The loopholes are glaring. While the treaty prohibits nations from claiming sovereignty over the moon, it says nothing about corporations. Companies like SpaceX and Blue Origin aren't signatories, leaving them free to exploit ambiguity. In 2020, the U.S. signed the Artemis Accords, asserting the right to create safety zones around lunar operations, a move China and Russia decried as backdoor colonialism. Meanwhile, Luxembourg pioneered space resource rights laws, letting firms legally own whatever they mine off-world. The result? A gold rush scenario where overlapping claims could spark conflicts no Earth court can adjudicate. Weapons are the ultimate gray zone. The treaty bans military bases on the moon but doesn't define what constitutes one. Is a radar station military if it's labeled scientific? In 2019, India tested an anti-satellite missile, littering orbit with shrapnel that nearly hit the ISS. Because the treaty only bans WMDs, conventional arms testing is fair game, including China's shrouded, peaceful experiments with orbital grappling satellites that could yank rival spacecraft out of orbit. Even asteroids aren't safe. NASA's DART mission proved we can redirect them. The same tech could fling a city killer at Earth while calling it planetary defense practice. The worst part, there's no referee. The UN's Office for Outer Space Affairs has fewer staff than a mid-sized McDonald's and no authority to arrest or fine. When Russia blew up a satellite in 2021, creating debris that forced ISS astronauts into evacuation drills, the diplomatic response was a strongly worded memo. Private firms operate with even less oversight. Imagine a SpaceX Wang mining standoff where both sides cite conflicting national treaties while their autonomous drones face off over a lunar ice deposit. Solutions are as messy as the problem. Some propose a space NATO with shared enforcement, but getting rivals to agree on rules is like heralding cats in zero gravity. Others suggest blockchain land registries for mining claims, yet no algorithm can stop a rogue state from ignoring them. Until humanity patches these legal voids, the final frontier risks becoming a lawless Wild West, where the only rule is that there are no rules and disputes are settled not with lawyers but with whoever has the most drones in the right crater. Astronauts floating effortlessly in zero gravity might seem like the ultimate workout hack. No heavy lifting, no joint strain, just smooth movement through space. But that freedom comes at a horrifying cost. Without gravity's constant tug, muscles don't just weaken, they vanish. The human body, ruthlessly efficient, starts cannibalizing what it no longer thinks it needs. And the brutal truth, even 2-hour daily workouts barely slow the decay. Take Chris Hadfield's experience during his 5-month stint on the ISS. The Canadian astronaut was a fitness fanatic, logging marathon sessions on the station's modified treadmill and resistance machine. But despite the grueling routine strapped into harnesses, fighting against bungee cords, his body betrayed him. In footage from his final weeks in orbit, Hadfield's legs visibly shrink, his calves flattening like deflated balloons. The real nightmare began upon re-entry. After splashdown, he couldn't stand without assistance. "It felt like my bones were made of glass," he later admitted, describing how his muscles fired erratically, his nervous system scrambling to remember Earth's unrelenting pull. Rehabilitation took months, with therapists guiding his atrophied limbs through motions a toddler could perform. The science behind this breakdown is merciless. On Earth, standing upright engages dozens of muscles just to resist gravity, your calves, quads, and core constantly micro-adjusting. In space, those fibers go dormant, triggering a biological alarm. Within days, protein synthesis plummets. By week 2, astronauts lose up to 20% of their muscle mass, equivalent to decades of aging compressed into a fortnight. The most devastating losses strike the anti-gravity muscles along the spine and legs. MRIs reveal fibers not just shrinking but actually rearranging, their supportive weave unraveling like frayed rope. NASA countermeasures sound like medieval torture devices. The Advanced Resistive Exercise Device ARD forces astronauts to squat and deadlift against vacuum cylinders, simulating weights. But here's the catch: it only works for large muscle groups. Fine motor control, that's sacrificed. Hadfield described struggling to hold a pen post-flight, his forearm muscles so degraded they couldn't stabilize his grip. Even vibration plates touted as muscle saviors show mixed results. A 2019 study found they preserve bulk but not strength, leaving astronauts with muscles that look intact but function like wet paper. The cruel irony: exercise might accelerate some damage. Russian cosmonauts on Mir who overtrained often returned with worse tendon stiffness, their overworked fibers shortening like dried leather. Modern ISS crews now balance resistance work with low-impact cycling, but the gains are minimal. "You're not building muscle up there," admits former astronaut Scott Kelly. "You're just slowing the rate at which you lose it." Future Mars missions face a grimmer equation. 6 months in 0G could leave pioneers too weak to walk unassisted upon arrival, a death sentence if emergency evacuation is needed. Proposed fixes sound like sci-fi: skin-tight electrostimulation suits that force muscles to contract, or spinning habitats that trade nausea for gravity. But until then, every astronaut launching into space isn't just embarking on a mission, they're signing a Faustian bargain, trading their body's vitality for a ticket to the stars. The cosmos doesn't care how many hours you spend on the space treadmill. It's always counting down, silently dismantling you one muscle fiber at a time. Spacesuits might look sleek in sci-fi movies, but in reality, they're more like walking straitjackets than second skins. Every time an astronaut bends an elbow or lifts a knee, they're fighting against pressurized layers stiff as frozen rubber, turning simple movements into exhausting battles. The Apollo moonwalks revealed this danger in painful detail. Those iconic bunny hops weren't cheerful exploration. They were desperate adaptations to suits so rigid falling could mean death. When Charlie Duke of Apollo 16 nearly toppled backward near a lunar crater, his stiff torso couldn't twist fast enough to catch himself. Only a frantic one-armed push against the ground saved him from a suit rupture on razor-sharp regolith. His heart rate spiked to 180 not from exertion, but sheer terror at how close he'd come to becoming the moon's first permanent resident. Modern Artemis suits face an even tougher challenge. Mars gravity, 38% of Earth's turns falls into slow-motion disasters. Testing in NASA, a simulated Martian landscape, proved how deceptive this is. Volunteers in pressurized suits tripping at just 10 miles per hour hit the ground with the same force as a 25-mile-per-hour Earth crash. The latest XEMU suits try combating this with revolutionary bearings at the hips and knees, but footage from neutral buoyancy labs shows astronauts still moving like marionettes with tangled strings. A 2022 trial had a test subject spend 20 minutes just retrieving a dropped wrench, each finger motion requiring deliberate, muscle-straining effort against the glove's resistance. The deadliest limitation isn't in the limbs, it's the helmet's frozen stare. Current designs offer barely 110 degrees of peripheral vision, creating dangerous blind spots. Apollo astronauts reported losing their footing when they couldn't see waist-level obstacles, a problem magnified on Mars with its ubiquitous boulders and dust-hidden crevices. Next-gen helmets promise better visibility, but add another horror: amplified internal fogging. During a recent lunar analog mission in Arizona, An engineer wearing the prototype nearly collided with a rover when his visor fogged up during a temperature swing, a death sentence if it happened during an actual extravehicular activity with no one to guide him. Solutions sound deceptively simple. MIT researchers proposed electroactive polymers that stiffen or relax on command, like artificial muscles woven into the fabric. But early prototypes failed spectacularly during Mars chamber tests. One glove's smart joints froze solid at -130 degrees Fahrenheit, locking the wearer's fingers in a claw-like grip. Another approach takes cues from deep-sea diving exoskeletons, using hydraulic assist systems to reduce strain. The trade-off: 20 extra pounds of weight and a power pack that lasts just 4 hours. Every innovation solves one problem while creating another, trapped in an engineering loop where flexibility fights against the unbreakable law of physics. To keep an astronaut alive under vacuum, some stiffness is non-negotiable. Perhaps the cruelest irony lies in the astronauts' own bodies. Months in microgravity leave crews with weakened muscles and slowed reflexes precisely when they'll need peak agility to navigate alien terrain in these cumbersome suits. Training videos show even veteran astronauts stumbling during post-flight suit trials, their Earth-readapting bodies working against the very equipment designed to protect them. The first moonwalkers had it easy. Their biggest fall risk was a 4-foot tumble in 1/6 gravity. Mars explorers will face 8-foot drops into unseen pits, jagged rocks hiding under dust drifts, and the ever-present knowledge that one torn glove or cracked visor means bleeding out before help can possibly arrive. Spacesuits aren't just outfits, they're miniature spacecraft with a horrifying catch: the safer they make you from the environment, the more dangerous they make you to yourself. The most volatile threat to deep space missions isn't radiation or micrometeoroids, it's the fuel that's supposed to get you home, silently vanishing into the void. Cryogenic propellants like liquid hydrogen and oxygen don't just stay obediently in their tanks. They boil away molecule by molecule, escaping through insulation floors so tiny they'd make a pinhole look cavernous. This isn't a slow leak, it's a countdown to stranded. NASA Centaur Upper Stage, a workhorse since the 1960s, loses up to 4% of its liquid hydrogen per day just parked in orbit. On a 3-year Mars mission, that means watching helplessly as your return ticket evaporates before your eyes. The physics behind this is merciless. Hydrogen liquefies at -423 degrees Fahrenheit colder than Pluto's surface. Even the best insulation can't completely block heat creeping in from sunlight, equipment, or the spacecraft's own electronics. Every stray calorie that sneaks into the tank turns liquid back into gas, building pressure until relief valves blow precious fuel into space. The Apollo missions got lucky. Their short lunar trips meant boil-off was manageable. But when Lockheed Martin studied a hypothetical Mars mission in 2013, they found traditional tanks would hemorrhage 68% of their hydrogen before reaching the red planet. That's not an engineering challenge, that's a suicide mission. SpaceX's Starship tackles this with brute force innovation. Its stainless steel hull isn't just shiny, it's wrapped in a hexagonal quilt of ceramic-based thermal tiles, the same material shielding it during Earth re-entry. But the real breakthrough lurks beneath that armor, an invisible vapor shield. By sandwiching microscopic aerogel between tank layers, engineers created a barrier so effective it cuts boil-off rates by 80%. Early tests mimicked deep space conditions for months, with sensors tracking every molecule lost. The results shocked even SpaceX. Their new insulation could theoretically keep hydrogen liquid for a staggering 18 months without active cooling. Yet the solution introduces new nightmares. Aerogel crumbles under vibration, and Starship's violent launches risk shaking this fragile defense to dust. NASA Alternative Zero Boil-Off Technology, or ZBO, a system that catches escaping hydrogen with magnetic fields, reliquefies it using solar-powered cryocoolers and pumps it back into the tank. It sounds elegant until you realize the machinery weighs as much as a compact car and guzzles power like a data center. During a 2021 test on the ISS, a prototype ZBO unit kept hydrogen liquid for 6 weeks but required so much electricity, it drained backup batteries meant for life support. The cruel irony, the very thing making hydrogen ideal for spaceflight, its lightness, also makes it the leakiest. Alternatives like methane are easier to store but pack less punch. Nuclear thermal propulsion sidesteps cryogenics entirely, but no one wants a reactor strapped to their crew module. For now, every deep space mission walks a razor's edge. Pack enough fuel to account for losses and the ship becomes too heavy to launch. Pack too little and you're left floating among the stars with empty tanks, watching your breathable air dwindle alongside your hope. The universe doesn't care about elegant engineering. It simply asks, how much of your future are you willing to watch evaporate before your eyes? There's a reason NASA keeps vomit bags stashed in every corner of their spacecraft, because space doesn't just attack your bones and muscles. It hijacks your very sense of direction, turning the inner ear's delicate balance system into a traitor. Astronauts call it space adaptation syndrome, but the symptoms sound like a bad hangover meets a carnival ride from hell. Sudden nausea, cold sweats, a spinning sensation so intense some victims report feeling like their brain has come loose inside their skull. Footage from the infamous Vomit Comet, NASA, a zero-gravity training plane, shows even seasoned flyers reduced to clutching their stomachs as their bodies rebel against the impossible truth that up and down no longer exist. This isn't just motion sickness on steroids. It's your vestibular system, the fluid-filled canals in your inner ear that evolved over millions of years to rely on Earth's gravity, short-circuiting in real time. When you tilt your head on Earth, tiny hairs in these canals detect the movement, sending signals to your brain that keep you oriented in microgravity. That fluid floats aimlessly like a buoy unmoored in a storm. The result, your brain receives garbled messages, your eyes say you're floating, your muscles report weightlessness, but your inner ear screams that you're tumbling head over heels. The numbers are brutal. 60% of astronauts suffer from space adaptation syndrome, with symptoms peaking within the first 48 hours. Apollo astronaut Frank Borman spent his first day in orbit vomiting so violently, mission control debated aborting the mission. Years later, shuttle veteran Jake Gahn became so incapacitated, his crewmates jokingly created the Gahn scale to measure nausea, with 1 Gahn equaling total incapacitation. Modern crews prep with anti-nausea drugs, but the medications often backfire, causing drowsiness or blurry vision. Dangerous side effects when you're operating a billion-dollar spacecraft. The real terror kicks in during emergencies. Imagine trying to locate a fire or a leaking air valve while your brain insists the room is upside down. Cosmonaut Gennady Padalka described the horror of floating toward what he swore was the ceiling during a midnight alarm, only to realize too late that his disoriented body had actually been drifting toward a critical equipment panel. He smashed into its shoulder first, leaving a dent in the metal and his arm bruised for weeks. Recovery isn't guaranteed. Some astronauts adjust within days, but others, like NASA's very first scientist astronaut, Joe Kerwin, endured weeks of misery. Kerwin's diary from the Skylab mission reads like a medical thriller. Day 12, still dizzy when I turn my head too fast. The station tilts around me like a funhouse mirror every time I close my eyes. Even upon returning to Earth, many face readaptation syndrome. Their Earth-trained vestibular systems now struggling to recalibrate after months in orbit. Solutions range from quirky to borderline sci-fi. Russian cosmonauts swear by pre-flight vestibular conditioning, a spinning in chairs while tracking moving dots to train their brains. NASA experiments with vibrating forearm pads that provide artificial gravity cues, tricking the brain into focusing on tactile feedback instead of the inner ear's lies. But the ultimate fix might be the simplest: time. The brain eventually stops fighting the new reality, rewriting its own rulebook to accept that in space, the only true down is whatever surface your feet happen to touch. Until that moment comes, though, every new astronaut learns the same hard lesson: space doesn't just push your body to its limits. It plays tricks on your mind, turning the very act of floating into a battle against your own biology. And the casualty count isn't measured in broken bones or radiation doses, but in hundreds of filled vomit bags, silently cataloging humanity's awkward first steps into the cosmos. A single bolt the size of your thumb doomed 7 astronauts. That's the brutal lesson of February 1st, 2003, when Space Shuttle Columbia broke apart over Texas, not from some dramatic explosion or cosmic catastrophe, but because a piece of foam insulation, shaken loose during launch by vibrations no one thought dangerous, punched a hole in the wing's leading edge. That gap, no wider than a dinner plate, became a death sentence 16 days later, allowing superheated plasma to slice through the shuttle's aluminum skeleton like a blowtorch through wax. The chilling truth: spacecraft are only as strong as their weakest component, where a 17-centimeter foam fragment, a frayed wire, or even a stripped screw thread can cascade into catastrophe. The engineering term for this nightmare is single-point failure, a component with no backup, no redundancy, whose failure guarantees system-wide collapse. Columbia's wing had no secondary thermal shield. The Apollo 13 oxygen tank that exploded in 1970 had no backup fuse. Even the Soviet Soyuz 11 capsule's fatal valve leak in 1971 traced back to one flawed seal, its tiny defect invisible until the vacuum of space ripped it open. These aren't freak accidents, they're the universe exploiting a fundamental truth. In the harsh economy of space travel, every gram counts, and engineers constantly gamble on which parts can't afford to fail and which might. Modern spacecraft fight this risk with ruthless redundancy. NASA Orion, built for lunar missions, carries quadruple redundant flight computers. If 3 fail simultaneously, the 4th can still guide the crew home. Its vital systems follow a 2-fault tolerance rule, 3 independent backup layers ensuring survival even after 2 catastrophic failures. Take the oxygen system. If the primary tanks leak, secondary cartridges activate. If those fail, chemical scrubbers recycle cabin air. If even that falters, astronauts can tap the spacesuit's portable reserves. This obsessive duplication adds weight, costs millions, but for good reason when your life depends on a valve not sticking or a circuit not shorting. Good enough is a death wish. Yet redundancy has its limits. You can't double every bolt or triple shield every wire without turning the spacecraft into an immovable brick. The Artemis program's lunar lander faces this dilemma head-on. Its aluminum fuel tanks use fail-safe weld joints designed to leak slowly if cracked, buying time for repairs. But critics argue this merely trades instant catastrophe for delayed disaster. Meanwhile, SpaceX's Starship takes the opposite approach, accepting certain single-point failures like its methane fuel header tanks, while designing the entire vehicle to be so mass-producible that losing one in testing is tragic but not program-ending. The cruel irony: the safer we make spacecraft, the more complacency creeps in. After 30 years of shuttle flights, NASA grew accustomed to foam shedding until Columbia proved that familiarity breeds blindness. Today's engineers walk a razor's edge between over-engineering that stifles progress and under-preparing that courts tragedy. Every bolt tightened, every wire inspected carries the ghost of those 7 astronauts, reminding us that in space there are no small mistakes, only consequences we haven't met yet. Moon dust doesn't just coat surfaces, it attacks them, clinging with an otherworldly grip that defies physics as we know it. The Apollo astronauts quickly realized this wasn't ordinary dirt. Lunar regolith is razor-sharp, electrostatically charged by relentless solar wind bombardment, and it behaves more like a malicious poltergeist than inert soil. When Gene Cernan of Apollo 17 raked his glove through the moon's surface, the dust didn't drift away, it leaped onto his suit as if alive, smearing every crease and joint with a gray-black paste that refused to brush off. Cameras, solar panels, even helmet visors became fogged with this abrasive grit, turning crisp lunar panoramas into hazy nightmares. But the real crisis struck when their rover's fender broke, sending a rooster tail of dust spewing over the astronauts and their equipment. What followed wasn't just an inconvenience, it was a masterclass in improvisational survival. The footage from that moment is equal parts hilarious and horrifying. With the rover's unprotected rear wheel kicking up a continuous dust storm, Cernan and Harrison Schmitt found themselves driving blind, their suits and instruments caked in fine particles that obscured dials and clogged mechanisms. Every movement stirred more dust, creating a feedback loop of contamination. In a desperate fix, they duct-taped laminated maps to the broken fender, a makeshift shield that barely worked. Later, Schmitt described the dust as pernicious, infiltrating their lunar module's cabin despite rigorous brushing at the airlock. Once inside, it floated in the microgravity like smoke, irritating their eyes and lungs, and leaving a gunpowder-like stench they could taste for days after returning to Earth. What makes this dust so diabolical? Unlike Earth's weathered particles, lunar regolith has never been smoothed by wind or water. Billions of years of meteoroid impacts have shattered it into jagged, glass-like shards with fractal edges that cling relentlessly to surfaces. But the real culprit is the sun. Unfiltered by an atmosphere, solar radiation bombards the moon's surface, stripping electrons from dust grains and leaving them electrostatically charged. This isn't static cling like your socks fresh from the dryer. It's a relentless, subatomic level attraction that makes the dust stick to everything like cosmic Velcro. Apollo crews found it impossible to fully clean their suits. The dust clung to seals, abraded knee joints, and even shorted out equipment. Fast forward to modern lunar ambitions, and the problem remains unsolved. NASA Artemis missions will face even greater exposure, with plans for extended stays and pressurized rovers that could become dust traps. Testing in vacuum chambers reveals that lunar simulants don't just coat surfaces. They embed themselves, grinding into fabrics and scratching lenses beyond repair. A single dust-coated glove touch could transfer enough abrasive particles to cripple a rover's optics or jam a spacesuit's bearings. Proposed solutions sound like mad science: electrostatic brushes that repel dust with opposing charges, or magnetic filtration systems that exploit the dust's ion content. But until then, every moonwalker will wage a silent war against an enemy that's as persistent as it is pervasive, a reminder that even the smallest particles in space can become mission-critical threats when they refuse to let go. Beyond Earth's protective magnetic bubble, there's an invisible storm raging, one that makes solar radiation look like a gentle drizzle. Galactic cosmic rays aren't your typical protons or electrons. These are atomic nuclei hurled across the galaxy by supernova explosions, moving near light speed with enough energy to punch through solid lead like it's tissue paper. The deadliest among them, iron nuclei, packing 56 times the mass of a proton, they rip through spacecraft shielding and human cells with equal indifference. When one of these microscopic freight trains slams into DNA, it doesn't just cause damage, it sprays chromosomes with subatomic shrapnel, triggering mutations no earthly radiation can replicate. NASA Brookhaven National Laboratory revealed the gruesome details in a series of experiments that should terrify any future Mars traveler. Researchers exposed mice to simulated galactic cosmic rays in a particle accelerator, then watched as their brains literally rewired themselves into dementia factories. Within months, the mice showed plaque buildup eerily similar to Alzheimer's in humans, amyloid proteins clogging neural pathways. Memory tests failed spectacularly, and once curious rodents became disoriented shadows of themselves. Autopsies revealed the iron nuclei hadn't just killed brain cells, they'd triggered a cascade of inflammation that continued destroying tissue long after exposure. The lead scientist summarized it with chilling simplicity. It's like accelerating decades of brain aging into weeks. What makes these particles so insidious is their ability to bypass our best defenses. Earth's magnetic field deflects most, but astronauts venturing to the Moon or Mars lose that protection. Aluminum hulls might stop solar flares, but galactic cosmic rays laugh at mere metal. They spark secondary radiation when striking hulls, creating a deadly shower of fragments inside the spacecraft itself. Astronauts report seeing light flashes during quiet moments, their retinas being bombarded by these particles, even with eyes closed. The Apollo crews experienced this constantly. Their few days in deep space exposed them to more high-energy nuclei than ISS astronauts accumulate in 6 months. The long-term implications are even darker. Unlike radiation on Earth, which primarily risks cancer, cosmic rays seem to attack the nervous system itself. A 2018 study tracking ISS astronauts found disturbing cognitive declines, slower reaction times, fuzzy memory recall, and reduced problem-solving skills that lingered for years post-mission. Brain scans showed worrying similarities to early-stage neurodegenerative disease. Proposed countermeasures sound like sci-fi. Liquid hydrogen shields that absorb particles before they fragment, or magnetic deflector shields stronger than Earth's own field. But until those exist, every interplanetary voyage is a gamble, not just with cancer risks but with the very essence of what makes us human, our ability to think, remember, and recognize our own reflection. The cruelest twist, these particles are everywhere in space, impossible to predict or avoid. A single iron nucleus from a long-dead star could be streaking toward your prefrontal cortex right now. A microscopic bullet fired billions of years ago, with your name written on it in subatomic ink. For future Mars colonists, this isn't abstract physics. It's the silent question hanging over every sunrise on the red planet. Will my mind outlast my body? The universe seems determined to erase us twice over, first our flesh, then our memories. Sunlight isn't just illumination in space, it's life support. The moment shadow falls, temperatures plummet faster than a rock dropped from orbit, turning spacecraft components into brittle ice sculptures. This hidden killer doesn't need explosions or radiation to strike. All it requires is an eclipse, a crater's shadow, or even a rover parking slightly too far into the shade. The Israeli Bereshit lander learned this the hard way in 2019. During its final descent to the Moon, a brief computer reset triggered by a misaligned sensor sent the craft spiraling. As engineers scrambled to regain control, another disaster unfolded silently. The lander's metal skeleton, suddenly deprived of sunlight during the maneuver, contracted so violently that critical fuel lines fractured. By the time the engines fired again, it was too late. Bereshit smashed into the lunar surface at 300 miles per hour, its systems flash frozen in the darkness. Autopsies revealed the chilling truth: this wasn't just a software crash. It was a death by degrees, literal ones, as the cold's invisible grip shattered the mission in seconds. The physics behind this are merciless. In space, there's no atmosphere to buffer temperature swings. Sunlight can heat surfaces to 250 degrees Fahrenheit, but shadow plunges them to -250 just as fast. Metals contract, lubricants solidify into glue, and batteries lose up to 70% of their efficiency. NASA Mars rovers battle this daily. Their solar panels can't generate power in darkness, risking frozen electronics. That's why Opportunity and Spirit carried radioactive heaters, their plutonium-238 cores glowing warm like miniature suns through the frigid Martian nights. When a global dust storm blocked sunlight from reaching Opportunity's panels in 2018, those heaters weren't enough. Temperatures inside the rover dropped so low its circuits cracked, ending a 15-year mission not with a mechanical failure but with a silent, creeping cold. Modern spacecraft fight back with ingenious solutions. The Perseverance rover's batteries are wrapped in aerogel blankets materials so insulating they could shield your hand from a blowtorch. Lunar landers now embed flexible heating strips along fuel lines, their thermostats tuned to react faster than human reflexes. Even the ISS has its own version of this war, when orbital night cuts solar power for 45 minutes 16 times a day. Lithium-ion batteries kick in, warmed by dedicated heaters to prevent catastrophic discharge. But the ultimate test is coming: Artemis's lunar base, where 2 week nights will turn habitats into freezers without nuclear-powered thermal units. Concept art shows underground lava tubes as natural insulation, but colonists will still face a brutal equation: lose power for even 12 hours, and your life support systems could ice over like a windshield in Antarctica. The irony: Earth eclipses are beautiful spectacles. In space, they're silent assassins. 1 minute you're basking in stellar warmth, the next you're stranded in a darkness so cold it physically shrinks your ship around you. Future explorers won't just watch for solar flares or micrometeoroids, they'll eye every shadow like a predator. Knowing the difference between life and death might be as simple as parking 3 feet to the left. Imagine trusting an AI to guide your spacecraft through the asteroid belt, only to watch helplessly as it steers you directly into a collision course. This isn't the plot of 2001, A Space Odyssey. It's a real-world dilemma facing modern missions as space agencies increasingly hand the reins to artificial intelligence. The Perseverance rover's autonomous navigation system is a marvel of engineering, capable of picking its way across Martian terrain without a single human command. But what happens when these systems fail in deep space, where a single misjudgment could leave astronauts stranded millions of miles from help? The contrast between sci-fi nightmares and current tech is stark. HAL 9000 mutiny in 2001 was pure fiction, but its underlying theme, blind trust in machines, isn't. Perseverance relies on AI for tasks like avoiding rocks or selecting drill sites, with humans light minutes away. So far, it's worked flawlessly, but Mars is a forgiving playground compared to the stakes of crewed missions. In 2021, an experimental AI piloting a simulated lunar lander repeatedly crashed into unexpected terrain because its training data lacked certain rock shapes. The system wasn't defective, it was simply unprepared for the infinite variables of space. The real danger isn't malevolent AI, it's overconfidence. Modern spacecraft use machine learning for everything from diagnosing equipment failures to managing life support. These systems excel at handling predictable scenarios but falter when faced with the unknown. Like the time a Russian Progress cargo ship's docking AI mistook the ISS's reflective insulation for open space and nearly collided with the station. Crews had seconds to override it manually. On a Mars mission, that delay could stretch to unbearable minutes. Proposed solutions walk a tightrope between autonomy and control. NASA Artemis program plans to use AI as a co-pilot, suggesting landing sites while humans make final calls. SpaceX's Starship, meanwhile, leans heavily on automation for orbital maneuvers, a necessity given the complexity of its methane-fueled dance. But every layer of AI introduces new failure points. A 2023 study found that neural networks interpreting satellite imagery could be tricked by adversarial attacks, subtle pixel changes invisible to humans but catastrophic for navigation. The ultimate question isn't whether AI will fail, but how much leeway we give it when it does. Future colonists might rely on algorithms to grow food or purify water. Systems too complex for quick human intervention. Lose those and you're not just troubleshooting a glitch, you're fighting for survival with a digital ghost as your only lifeline. The stars may demand we trust our silicon companions, but history whispers a warning. No machine, no matter how brilliant, can replace human instinct when the void comes calling. As we tally up the 30 deadliest dangers lurking in the cosmos, it's not just about fear, it's about survival priorities. Number 30. Cosmic dust clinging to spacesuits like toxic glitter. 29. AI navigation glitches stranding crews in the void. 28. Solar storms frying electronics mid-flight. The countdown narrows to the nightmare scenarios. Top 10. We hit the big leagues. Number 10. Bone density evaporating faster than water in vacuum. 9. Time dilation tearing at social bonds across planets. 8. Frozen fuel lines shattering in shadow. 7. Muscle atrophy turning astronauts into ragdolls. 6. Radiation storms shredding DNA like confetti. 5. Psychological isolation eroding sanity. 4. Single-point failures dooming missions. 3. Lunar dust as abrasive as ground glass. 2. Cryogenic fuels boiling away into nothingness. And the number 1 threat. Complacency. The moment we forget space isn't just a frontier, but a predator with infinite patience and zero mercy. Yet every horror on this list sparks humanity's genius. Solar storms birthed radiation-shielded habitats. Bone loss led to artificial gravity experiments. Even lethal moon dust drives innovation in electrostatic repulsion tech. The International Space Station's urine recycler, a marvel born from necessity, now inspires Earth's water-scarce regions. SpaceX's self-healing metal alloys. A direct response to micrometeoroid strikes. These aren't just solutions, they're stepping stones to the stars, each danger conquered unlocking new horizons. Picture Mars colonies with underground gardens fed by repurposed astronaut waste, or lunar factories churning out solar panels from moon dust itself. The universe throws obstacles in our path not to stop us but to force us to evolve. So which danger shook you the most? Was it the silent creep of cosmic radiation, or the psychological abyss of deep space isolation? Drop your thoughts below, because this conversation isn't just about surviving the cosmos. It's about thriving in it, transforming every threat into a testament of human ingenuity. The void may be indifferent, but we're just getting started.